cool. Oh, it's a little single board microcomputer. Primarily just for fun, maybe for educational purposes. I would love to teach a class on it actually, but it doesn't really fit into a curriculum. But I will give you details as it develops. All right, any questions so far? We've been talking about phrase structure grammars. Yeah, I think it would be a cool class. I want to go over the homework that I just graded a few days ago and then continue working with Turing Machines. But any questions up front, we can talk about those first. All right, well, let's just run through some of the graph theory questions on your latest homework. So let me pull up a copy of this. So as usual, I graded a collection of problems, but not every question. So I did not grade question 1 because if you can do questions 2 and 3 and so on, then you probably understand adjacency matrices, and that's the main thing I wanted you to understand. So question 1 I did not grade. Question 2, an undirected graph for the following adjacency matrix. So you've got 3 vertices, 3 nodes, which you know because your matrix is 3 by 3. And an adjacency matrix will always be square, right? N by n for a graph with n vertices. And so whatever we choose to call these, if we just call them A, B, C, we have an edge from A to B and an edge from B to C. And it's symmetric because it's undirected. And so this ends up looking pretty simple. Just something like this. So pretty reductionist graph. And then in question 3, it changes to a directed graph. So I graded 2, I graded 3, I graded 4, I graded 6, and I looked at 7, and I graded 8. So a directed graph, depending on how you label these, if you label these A, B, C, D, A, B, C, D, and then if we suppose that the row is the edge you're coming from, the vertex you're coming from, and the column is the one you're going to, then we have 4 vertices, A, B, C, D. And this first row says there's an edge from A to A. So you can draw this with 2 arrows or 1 arrow and so on, but it's a loop basically. And there's also one from A to B, and there's also one from A to C. And then the second row would be vertex B, and there's only one edge from B to C. So you get that. And this third row is vertex C, so there's an edge from C to A. So that's bidirectional. And then another loop where C goes to C. And then the last row would be the 4th node, which I labeled D, and there's an edge from D to A. And another one from D to B, and then one from D to C. And so that would be a way to draw your graph. Now the graph you come up with might be totally different in appearance, but it should have similar properties. It should have 2 loops. It should have a total of 9 edges. And you can tell there's going to be 9 edges because there's 1, 2, 3, 4, 5, 8 edges, because there's a total of 8 ones in this matrix. And there'll be 2 vertices with 3 arrows coming out of them, and 2 vertices with a single arrow, and so on. All right, question 4. I think everybody got this, which is awesome. This is usually a really hard concept for people. You have two matrices, 1, 0, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 0, 1, 0, 1, 0, 1, 1. And I said to label this first one with A, B, C, and the second one with X, Y, Z. And if you draw the graphs, what do you have? You have A, B, C, X, Y, Z. So we have a loop from A to A, and we have something from A to C, and we also have something from B to C. And over here we have a loop at X and also a connection to Y and Z. And Y also has, oh, this looks weird. That's a 0. So we have a loop at X and a connection to Y, and Y has a connection to Z. So those are our drawings corresponding to those matrices. And you can eyeball these and see that these look the same, right? If I took this and I kind of like flipped it over and pulled the Y down, they would look like the same picture. And so if I want to find an isomorphism that's a mapping from this set of edges to that set of edges, it looks like if I took A over to X, and then that should be connected to exactly one vertex. Over here it's called C, over here it would be called Y. And that vertex would be connected to exactly one vertex, B here, Z there. That looks like it would preserve this connectivity, this notion of when one edge is connected to another. So we can define a mapping from this set to that set. And one way to define a mapping is just to show what each element here is carried over into that set. So this map would take A, in this case, to X. It would take B to Z. And it would take C to Y. So there's an example of a mapping. That's a symbol phi. That's used a lot of times for isomorphisms. I don't know why. It's just a Greek letter. You can use any letter you like. So that's an isomorphism. And you know, you could also say, yeah, it does get used in calc. You could also say, you know, phi is a function that takes A to X and B to Z and C to Y, for example. And I totally messed up my drawing. There's also a loop from B to B, and over here there's also a loop from Z to Z. Why didn't we get marked down if we didn't use phi but still got the idea across, right? Yeah, you can use any symbol you want. Usually we just use F or something for that. What I was really looking for was this information, right? You should map A to X and B to Z and C to Y. And there's a different mapping that we could also use. We could also map A to Z and C to Y and B to X. And that's an equally good mapping. Alright, so that was the isomorphism question. I did not grade number 5, But let's look at it. So for the following ordered list of vertices, indicate whether or not it represents a path. So A, B, E, C, B. A, B, E, C, B, that is a path. Right? It's a path if starting from the first one you can visit each vertex in order by following edges. So that first one is a path. What is its length? Well, from A to B is 1, B to E is 2, E to C is 3, C to B is 4. So this path has a length of 4. And you can convince yourself pretty quickly, I think, that the length of a path will be the number of vertices listed minus 1. Because we don't count, A as a length of 1. It's really from A to B is 1, and then 2, 3, 4. So if it's a path, the length will be the number of vertices minus 1. Is it a simple path? Yes, because we don't go over an edge more than once. And it's not a circuit, because to be a circuit we would have to end at A, and instead we ended at B. AD, ADA, so A to D to A to D to A, that is a path, right? Starting from A, we can move to each vertex in the list in order by following an edge. So that is a path, and its length is going to be 4. From A to D is 1, back to A is 2, back to D is 3, back to A is 4. So the length is the number of edges traveled along, exactly. And even though, we ended up right back where we started, right, you can take a journey of 100 miles and end up right back where you began. Every vacation is basically like that. You might fly to Hawaii and come back, and your total distance that you traveled is thousands of miles, right? But your distance from the start is 0. That's okay. So it's the total number of edges that you travel along. And that is a simple path. That's not a simple path because you traveled an edge more than once. It is a circuit because you start and end at the same point. And then this third one, ADB, well, you can go from A to D, but there's no edge from D to B, so it's not a path. Since it's not a path, you don't have to tell the length. Since it's not a path, you don't have to know if it's a simple path. And if it's not a path, it can't be a circuit. So B is a circuit because you end at the same part you started. Well, yeah. I guess it's not a simple circuit, but technically it's a circuit. I'm not going to ask you these questions. I'm going to ask you about Euler paths and Hamilton paths on the exam. But these get into kind of non-standard terminology. And then A, B, E, C, B, D. So there again, there's no edge from B to D. So not a path, no length, not a simple path. And not a circuit because it's not a path. All right, so 6 is looking at Euler paths. So is there an Euler path? An Euler path would have to travel along every edge exactly once. And the trick that we discussed for finding an Euler path is, see if there are any vertices with an odd degree. So vertex A has a degree of 3. Yeah, you can use lecture videos on the exam. This class is lecture videos, yeah. Final exam, yeah, final exam is cumulative, so it covers everything from day 1 forward. So to have an Euler circuit, so total degree of node A is 3, total degree of node B is 4, that's even, D is 5, that's odd, C is 4, which is even. So if there is an Euler path, it's going to have to start or end at A, and then either end or start at D. And so you can kind of just start following arrows. So I can go from A to B to C to A, and then come back down to D and hop out to C and back to D, and then hop up to B and hop back to D. So this will definitely have an Euler path, does not have an Euler circuit. And we know that because to have an Euler circuit, all the degrees of all the vertices has to be even. And then for 7, a Hamilton circuit, we'd need to visit every edge, every vertex exactly once, beginning and ending at the same point. And this is the same thing as what we discussed with some examples in class. Basically, a hand-wavy explanation, right? If we start at F, we'll have to visit E next, and the only way we can ever get back to F is by visiting E again. And if we visit E twice, it's no longer a Hamilton path. So there's not going to be a Hamilton circuit if we start at F. If we start anywhere else, we're going to have to eventually visit F, and we can only do that through E. And once we visit F, we can't visit E again. So F would have to be the last vertex that we visit, and if it's going to be a Hamilton circuit, F would have to be the first vertex we visit. And we just said we can't find a circuit if we start from F. So that's kind of a hand-wavy why there's no Hamilton circuit. Yeah, I'll post a quick synopsis of topics on Canvas before Friday. And we'll probably spend Friday just doing review. In fact, let me make a note. Yeah, you are welcome. All right, so question 8, Dijkstra's algorithm. So most people seem to have the right idea of this, and some people copied over this picture from one step to the next, which makes it very easy to see what you're doing. Some people did not, and I tried to figure out from what you wrote the order in which you did things, but sometimes it wasn't entirely clear. So let's go through this example in as much detail as we can bear. So I'm going to put down the vertices, and I'm going to put down the weights. Yeah, that was a chalkboard. Sounds like a typewriter. Cool. All right, and so we're trying to go from node A to node F. And let's see. Similar to a typewriter, but harder to hang on your wall. All right, so remember our algorithm is basically 2 steps. So first we set tentative distance of infinity. And we visit the start node with a distance of 0. So there's our graph, and the way we begin this, we visit our start node with a distance of 0, and the way we get to this node is we just visit node A, and we put down tentative distances of infinity everywhere. You can put a 0 by node A, that's fine. So it's important to know which node you are visiting right now, because that's the node from which we're going to relax adjacent nodes. So here's our 2-step process. Relax adjacent nodes, and then visit closest node. Alright, so we start off by visiting the node we're beginning from. So our first step of this procedure is to relax adjacent nodes. Adjacent to what? Adjacent to the node that we are now visiting. Okay, so we're visiting this node here, so we're going to relax the distances to any nodes directly connected to A. And relaxing doesn't mean just replace this with a number. It says calculate the distance knowing that I can get here in a distance of 0, and from there to B is 2, 0 plus 2 is 2. If that's smaller than my tentative distance, change the tentative distance. So 2 is smaller than infinity, so this becomes a 2. And the path is the path to A, followed by visiting this node B. And 0 plus 3 is 3, that's better than infinity, so I can get here in a distance of 3, starting from A and going to C. Okay, at this point, I would move to a new copy of your picture, because my next step is to visit the closest node, which means I'm going to circle it, and if this is the first picture I see and there's 2 nodes circled, I don't know which one you visited first. Yeah, 3AC works fine. I'm not worried about the formatting of this. But you should have information with the tentative distance and the path that gets you there at each vertex, except for the vertices with a distance of infinity, because we don't know how to get there. All right, so let me be a good role model student here. And let me make copies of this. And so this is 2, 5, 2, 3, 5, 1, 4, 2. And we visited this. That's A0. We visited B. That's AB. For a distance of 2, we visited C. That's AC with a distance of 3, and all of these are infinite. All right. So we visit the closest node to our collection of visited nodes. This is a node with a distance of 2, this is a distance of 3, all of these are infinity. B is the closest node, so we're going to visit that. So I circle that to say we're visiting that node now. And now we relax the adjacent nodes to B. So we don't relax a node we've already visited, but 2 plus 5 is 7, that's better than infinity. So this will be 7 by following A, B, D. 2 plus 2 is 4, so that's a good distance. This is A, B, E for a distance of 4. And that's it for nodes that are adjacent to B. AC3. Trying to remember that. I played an American Revolution game that I could never get the hang of. Oh yeah, Assassin's Creed. Yeah, I always got stuck in the bars in Boston, and I'd be like looking for someone I was supposed to like coordinate with, and I'd end up getting pukey and either like stop playing or I just like randomly take out my sword and get arrested. But I think if I had played the earlier versions, I might have had more success. I also needed to read the backstory because every now and then I'd end up back in that weird beginning part where there's like, you know, the time travel set up and all the weird technology, and I have a feeling I could have done things at that part, but I didn't really know what I was supposed to be doing. All right, so here's our picture right now, and we need to find the closest node and visit that. So 3, 4, 7, infinity, this is our closest node. Right? And if I can see the sequence, right, it's pretty clear. First you started at A, and then you visited B, and then you visited C. And that's important, right? The order of these is a key part of the algorithm. So we'll visit C, and now we need to relax adjacent edges. Now I can get here in a distance of 3, and 5 more gets me to E. That's 8. 8 is not better than 4. I've already got a solution that gets me to E in 4 steps, right? A, B, E. So I'm not going to use this solution A, C, E, because that's longer, and we're looking for the shortest path. So I don't adjust this distance, right? So relaxing means if I find a distance better than this, I'll replace it. But since 8 is worse than 4, I'm going to leave that alone. And there's no other unvisited nodes adjacent to C, so that's all I do for that step. All right, so let's do another one of these. And like I say on the exam, I'll give you a page with multiple copies of your original graph with the weights written in, so you don't have to do this part during your exam time. All right, so this was visited, this was A0. B is visited, that's AB2. C is visited, that's AC3. D is AB, D7. E is AB, E4, and F is still infinity. All right, so which node do I visit next? Exactly, E, or echo, right? And this was one point where some people misstepped. So this is a distance of 4, 7, infinity. 4 is the closest, so this is the node we're going to visit next. And then we're going to relax distances from 4, so 4 plus 4 is 8, better than infinity, so A, B, E, F for a distance 8. And E is a distance of 4, 1 more gets us to D, 4 plus 1 is 5, that's better than 7. So we're going to relax this too, and we're going to say A, B, E, D, and that's a distance of 5. Right? And we found a path to F with a distance of 8, right, from A to B to E to F. But until we mark this node as visited, we don't know that that's a shortest path. And in fact, it's not. So I told you not to do this on your test, but I'm going to do this anyway. I'm going to draw a little arrow and continue on the same page. So you only visit one node per drawing, exactly. All right, so now we visit the closest node. That's going to be this one. And we relax adjacent vertices, and so 5 plus 2 is 7. That's better. So this will be A, B, E, D, F for 7. And then, you know, I would make one more drawing and I'd have one vertex left. I'd circle that. That's going to be my final answer. So A, B, E, D, F, distance of 7. Right? And this is, you know, 1, 2, 3, 4 edges. Our previous solution was 1, 2, 3 edges, but it was a longer path. Right? So shortest path, in this case, we're not looking at the number of edges, we're looking at the sum of the weights of the edges. And if we just wanted to find the shortest number of edges to get us there, that's a much easier algorithm. But since these things are weighted, we need something like Dijkstra's algorithm, or Prim's algorithm, or, you know, there's a number of approaches to this. All right, so questions about the logistics of doing Dijkstra. If you were interested in the shortest number of edges from one vertex to another, let's say from here to here, there's a pretty straightforward algorithm we can use. And this is very recursive, right? So think 222, right? Basically from our starting point, we have 2 edges coming out. So if we find the shortest path from here to our destination and the shortest path from here to our destination, whichever of those is smaller, if we add one more, we find the shortest path from this original node. And if we find a shortest path from here to the destination, our shortest path from the original node is simply, well, follow this edge to here and then do whatever that shortest path is from there to your destination. So it's kind of like Dijkstra, but it's a little simpler without the weights involved. And a pure recursion will solve this, and we can also do this without recursion by saying, you know, okay, well, there's 2 spots I can go to. Let's remember both of those. First of all, let's try to find the shortest path from here. And then I'll come back and I'll try to find the shortest path from my thumb. All right, so I have a new subproblem. Let's find the shortest path from here. Well, I could go here or I could go here. And so now I have 2 new subproblems. One is to find the shortest path from here. The other is to find the shortest path from here. Well, this gives me 3 subproblems. I could try to find the shortest path from here, here, or here. And whichever one is shortest, right, I can simply go from here to there in one hop. Well, you know, I've got 2 paths of 1 edge from here, so I can find a path of 2 edges from here, which means I can find a path of 3 edges from here, which means I can find a path of 4 edges from here. I have to repeat that from this vertex, though, and see what the shortest path is I can find. So that's recursion, or it can be stack-based processing, and so on. So there's lots of algorithms in graph theory, and that's also something you would study in an algorithms course. You can talk about things like spanning trees and stuff like that. And because graphs are in some ways related to trees, which are related to, you know, recursion and recursive solutions and dynamic programming and all of these other 222 topics, right? A good understanding and ability to work with graphs is helpful for, lots of different aspects of computer science. So it's a whole subtopic in itself, or a whole topic in itself. But we don't go much deeper than what we've already done. But just be aware there's a lot more out there. The other thing about graph theory is it's one of these subjects where really simple questions sometimes have really complex answers, and that's kind of fun. For example, how many graphs can you make with a certain number of edges and vertices? And that's an interesting question. If you just start drawing pictures and try to see how many different graphs, meaning not isomorphic, can you come up with a certain number of edges and vertices, and the combinations start to grow very quickly. All right, so back to Turing machines. We introduced Turing machines on Monday, and remember, it's this theoretical model of computing where we have this infinite magnetic tape and a read-write head, which can read a single character from the tape, write a single character, and a notion of state, and then a program which says if you're in a particular state and there's a particular character on the tape under the read-write head, then change the character to some other character, move the tape left or right, and go to a new state. And with that kind of weird model, we can actually implement any program that we can implement on anything we consider to be a computer. And so we cobbled together a two's complement program. Then we looked at some programs in a simulator for detecting palindromes and calculating prime malady and so on. And for Turing machines, I won't ask you to write Turing machine programs, but I would like you to be able to look at a Turing machine program and understand what it's doing, right? Apply that program to a sample input tape. But you probably won't see that on the exam, but it's a good thing to know. So this kind of, I won't ask you to write a prime number program or a binary tree balancing algorithm on a Turing machine. These Turing machines we've been talking about are sometimes called deterministic Turing machines. Okay, so the D is deterministic. What does deterministic mean? It means that it's predictable. It's not random. There's some procedure one could follow to decide what this machine is going to do. Right? This is what we want our computers to be mostly. We don't want them to do random things. If we say I equals I plus 2, we'd like to know I is going to be incremented by 2, not, J is going to be divided by 17. Right? So mostly we think about our computers as being deterministic. And so a Turing machine without a prefix in the front usually means a deterministic Turing machine. It's the kind of thing you would build in Engineering 250. But it turns out we can also talk about what's called an NDTM, and this is non-deterministic. And a non-deterministic Turing machine is a really interesting device. It's a device that we can't look at and know exactly what it's going to do ahead of time. You can't actually predict which step it's going to execute next, because there is a magic genie inside. Okay, there's this benevolent genie inside the machine that helps direct how the machine executes your program. And here's a way to think about this. We write programs in C, right? And think about, you know, a program where you're parsing input. So you're writing a program and the person's going to type something in, and you're going to write code, you know, which says, you know, did the person type a search command? Did the person type an insert command? Did the person type a delete command? Did the person type a help command? Did the person make an error? And we've written a bunch of programs like this in 224 and in 222, where you know, if character bracket 0 equals s, then we do something. If scanf input %d equals 1, then do something, right? So you remember this, right? And you know, if this. So if we've got 5 things we're checking for, maybe we'll get lucky and the first thing that we check is what the person actually typed in. Or maybe, you know, they made an error and we don't know that until we get to the very end, right? So the time it takes this program to execute depends on, you know, the order in which we write these statements, the order in which we check these different conditions. But imagine that there was a genie inside your C program, and the genie could decide which of these statements to check first. And this genie, being all-knowing, if the person said, hey, I want to delete something, it would say, oh, let's do this if statement first. And your code would say, if the person typed a D, hey, that's what they typed, right? Your code would run a lot faster. So a non-deterministic Turing machine is a machine which has this genie inside, this wizard, who somehow causes your code to run quicker by always doing the right thing first. Okay, let me give you another example. Is 1001 a prime number? Well, if you or I write a C program, what do? We try dividing it by 2, 3, 4, 5, 6, 7, and so on, right? And it's not until we get up to, you know, I think this is divisible by 7, that we find a factor. It's not divisible by 2 or 3 or 4 or 5 or 6. So if you had this magic wizard inside your computer, it could say, hey, see if it's divisible by 7. And you do one division and say, oh yeah, this is divisible by 7. It's 7 times 143. All right? So this wizard can speed up your programs. Okay? That's what a non-deterministic Turing machine is. It's a machine in which somehow something inside the system is able to make good choices as to how your program should be executed. Okay, and this is obviously a theoretical model. You can't buy these. But for studying classes of problems and difficulty of solving questions, this is an interesting mechanism to think about. So you wouldn't need the answer if we had the answer, yeah. And the genie can't necessarily, you know, answer all of your questions, but it can help guide your execution, right? So imagine you write an algorithm, but you've got, you know, 5,000 things you have to do before you get the answer. It might get you to do, you know, one thing that by itself gives you the answer, right? Like playing high-low. High-low theoretically takes order and operations, right? But if this genie could say, hey, ask them if their number is 42, and that's your first guess, hey, you know, you found the number in one operation. All right, so ignoring the weirdness of that concept, right? Why do we care about non-deterministic Turing machines? Let's look at the order of complexity of certain algorithms. Okay, so this is like big O notation, basically. And you know, some algorithms, like a bubble sort, is an order n squared. Searching an array of numbers with no sorting applied to the numbers, that's an order n. Searching a sorted array is order log n. right? If we have a trie of data, then it might, be order some small constant, something close to order 1. Or if we have a hash table, theoretically, that's order 1. So one of the most classic problems in graph theory is the traveling salesperson problem. So the traveling salesperson problem is the following. We have a graph. I don't actually know if it has to be complete, but usually we think about this as being a complete graph where there's a connection from every vertex to every other vertex. I think I've got them all. And we have weights associated with each of these edges. So and so on. So picture, if you'd like, a collection of cities in the US, and look at a map and figure out the straight line distance along the roadways from one city to another. So you can make a graph like this. Okay, and if this, or think of an airline map, right? So major cities, so there's always a path from one airport to another, right? And it takes, a certain distance or a certain amount of time or something like that. Okay, the goal of the traveling salesperson problem is the following. Starting at some particular point, you want to follow a path from one vertex to another in such a way that you visit every vertex and then return back to where you started. And it's okay if you go through a vertex more than once. Your goal is to visit each vertex at least once, right? So the name of the problem is you're selling vacuum cleaners or hairbrushes or whatever, and you want to, make a stop in each city, and you want to minimize your driving distance. So you're looking for a order in which to visit these vertices so that your total combined distance is as small as possible. Top left and top middle vertices. I probably missed some more too, but thanks. All right, so you want to minimize the total distance in order to visit all vertices. And we can describe an algorithm for solving this very simply, right? If you're starting from here, let's say you have, A, B, C, D, E, F, G. Let's say you have 7 cities. Okay, I'm going to start at vertex A. There are 6 possible cities I could visit next. I can go to B, C, D, E, F, or G. And whatever city I visit next, there's 6 possible cities I could visit after that. And whatever city I visit next, there's 6 cities I could visit after that. And if I'm going to do this in a way that I only visit a city once, right, we can put a bound on the total number of trips we're going to have to take, right? But if I start from A and I go to B, and then from B I go to C, and from C I go to D, and then to E, and then to F, and then to G, and then from G I go back to A, right? I can add up the length of each of those edges, and I can find the total distance for that particular journey. But from A, instead of going to B initially, I could go to C. And from C, I could go back to A or B or D, E, F, G, and so on. So enumerating all the possible paths you can take is pretty trivial. You could do it with a bunch of nested for loops. You could do it with recursion, right? But it's not hard to do because, you know, at each city that I'm at, I have, in this case, 6 other cities that I can go to next. And for each of those, I can add up, you know, the length of the trip from D to that city. And I just keep track of my running sum. And when I finally get back to A, I just say, hey, you know, how long was that trip? And across all of these possibilities, I take the shortest distance. So we can describe an algorithm for solving traveling salesperson. The problem is it's really expensive computationally. Okay, it's going to be something along the order of, I believe, n to the n. It might be n factorial, but it's something horrible. So when we study large classes of problems and we're looking at kind of a gross characterization of their complexity, there's one particular differentiation between complexities that we hear a lot about, which is, can something be done in the order of some polynomial time? So, you know, n is the size of our problem, right? We can say, can this be done, for example, order n squared, or order n cubed, or even order n to the 5,000th, right? All of these are considered polynomial time. This is a really big polynomial. You know, when n increases a little bit, this number grows by a huge amount. But it's still a polynomial. It's a polynomial of degree 5,000, but it's still a polynomial. On the other hand, n to the n is somehow fundamentally bigger. In particular, if n gets to be bigger than 5,000, this will be bigger than n to the 5,000th. If n is 1,000,000, this will be bigger than n to the 1,000,000th. So as n grows, this is eventually bigger than any polynomial. So that's the sense in which this is a really horrifying amount of time compared to even something as big as that. All right, so here's where this is all going. So if an algorithm can be solved in polynomial time, it's called a type P algorithm. So bubble sorts are type P. Insertion, deletion sorts, those can be solved in polynomial time. Inserting a node into a binary tree, that's logarithm n, which is better than, you know, n to the first, which is a polynomial. So that's also a type P algorithm. So it can be solved in, right, if you can solve it in something less than polynomial time, you can solve it in polynomial time. So algorithms of type P, you know, are pretty doable in some sense. On the other hand, something that requires, say, you know, n to the n, or n factorial, or n to the n to the n, is not a polynomial time. It's bigger than that. All right, so type P algorithms can be solved in polynomial time. We know an algorithm that solves them in polynomial time, or possibly better. Okay, can be solved. Let me put a little footnote here. When we talk about solving, what does that mean? It means solved by a deterministic Turing machine. On the other hand, if an algorithm can be solved, and let me put a different footnote here, in polynomial time, by a non-deterministic Turing machine. It's called NP. NP meaning polynomial time on a non-deterministic Turing machine. All right, this is getting very theoretical now. But if we can solve this algorithm in polynomial time on, you know, a Pentium processor, which is a deterministic Turing machine, then it's type P. If we could solve it in polynomial time on a Pentium that also had a magic wizard inside, then we could say that's an NP problem, solvable in polynomial time on this non-deterministic Turing machine. And traveling salesperson is an NP problem, it turns out. Because if we had a genie inside, we would not have to check every possible path starting from A. Yeah, there's 6 possible cities we could visit next, but what if this wizard said, hey, go and visit city B next? Okay, now go visit city F. Now go visit city D, right? It could direct us to follow the exact order of cities that gives us a shortest path. And we could find that on a first try. So I'm skimming over a lot of details. We would need to talk about what are called decision problems, yes/no questions. And we could basically ask the genie, is there a path shorter than length, 500? And if it says yes, it would give us a path that was shorter. And then we could ask, is there a path shorter than 499? And we can keep asking these yes/no questions till it says no, and then we found our shortest path. All right. So ignoring the details, of which there are plenty, traveling salesperson turns out to be an NP problem. All right, solvable in polytime if we have a wizard to help us. The question is, on a deterministic Turing machine, on a plain old Pentium processor, can we find a polynomial time solution to traveling salesperson? And nobody's been able to do this yet, but nobody has proven that you can't do it. So it's an open question. And this is a $1 million question. So can you find an algorithm to solve traveling salesperson on a plain Turing machine, so no funny wizard, in guaranteed polynomial time? Yeah, there's a lot of money around that. At the very least, there's a $1 million prize for that. But the more interesting part is, if you can prove that this is impossible, right? You got fame and glory. If you can actually find a polynomial time solution to this, you've just changed the world. And this is for any number n. So however many nodes you end up with. Okay, so why is this such an interesting question? Why does this change the world? So this is all in the theory of computation, right? And this is stuff that people with lots of letters after their name spend their days thinking about. We can solve TS in poly time on a non-deterministic Turing machine. So TS is NP. And there's a lot of problems that are NP. A lot of problems that you can solve in polynomial time on a Turing machine with a genie, but that we don't know how to solve in polynomial time on a plain old Turing machine. And traveling salesperson is one of those problems. Okay, here's the magic. It turns out that if you can solve traveling salesperson in polynomial time on a plain old Turing machine, you can take that solution and use it to solve a bunch of other NP problems in polynomial time. So there's polynomial problems and there's NP problems, and the question is, can any of these also be done in polynomial time? And it turns out that if you can solve one of these in polynomial time, you can solve a lot of these in polynomial time. And so there's this question of NP complete problems. And a problem that's NP complete, if you can solve any of those in poly time, you can solve all of them in polynomial time. And so a single solution to a traveling salesperson in polynomial time suddenly solves a huge number of very, very difficult problems in polynomial time. And this has profound implications for cryptography and secrecy and all these other things. And so let me see if I have a handy list. So NP complete problems, right? These are problems that could be solved in polynomial time if you can solve traveling salesperson. And so there's lots of graph theory problems, right? Click problems, things like that. Mathematical programming, knapsack problem with several variants. So if you've done 222, you know about the knapsack problem. Variations on TS. Solving two variable quadratic polynomials over integers. So now we're starting to get into some of the stuff that ties into things like crypto systems. Longest common subsequence problem, that's another one from 222. Battleship, Bejeweled, Candy Crush Saga, Donkey King. I don't know about Assassin's Creed 3, Zelda, Lemmings. I mean, all of these have equivalent versions to problems that would be NP complete, meaning that we could solve these in polynomial time. And if you solve any of these in polynomial time, I love that Metroid's on there, you can solve them all, right? And this is the magic and the attraction of this whole question of, can any of these be solved in polynomial times? And so you'll see this question, you know, is P the same as NP? And it's an open question. And if you can prove that this can't be done, you know, if you can prove that these are different, that there is, say, no polynomial time solution to traveling salesperson, you can prove this is not an equality. And if you find a polynomial solution to TS, then you've proven that this is an equality. So it's this whole, you know, house of cards that is either, you know, completely solid or ready to come tumbling down. And all you got to do is find one case that you can either prove or disprove, and you've got like a whole classification for all these different problems. So yeah, if someone does make a breakthrough, I'm pretty sure it would become public knowledge very quickly, assuming the person knew what they were doing, just because it would be so exciting. And you know, almost certainly there would be a lot of concern, particularly if P turns out to be equal to NP. There would be a lot of concern in terms of you know, internet commerce and security issues and things like that. And there's movies about this. I actually stumbled across, it was kind of a pretty bad movie on Amazon. It was called Traveling Salesman, I think was the name of the movie. And it was about a small group of mathematicians who solved this problem and sort of the consequences of that. And it wasn't as good as I wanted it to be, but you know, it was a good popcorn movie. and yeah, it's a world changer, and it's millennial prize money and all this kind of stuff. Um, and it's another one of these questions that you don't need to be a professional mathematician or computer scientist um, in order to understand the traveling salesperson question. I mean, it's an easy question for anybody who's ever traveled and looked at a map. Um, and lots of people come up with what they think are solutions to this, and we'll send those around, and so far everything that seemed like a solution has had problems in it, logical flaws in the proofs and so on. But nobody's proven that you can't find a polynomial time solution either, which makes you think, after all this time and effort, maybe there is a poly solution. And so that's an open question. And there's harder problems, right? There's problems that are so hard that even if all of these come crumbling down and can be solved in polynomial time, these problems out here still cannot be, right? And those are even more computationally intense. But the NP complete ones could actually turn out to be all doable in poly time. All right, so that's a classic open problem in theory of computation, and you can Google and quickly find a lot of wormholes to lose yourself in around that. I wish math were cooler more often. Yeah, there was a good movie a while ago called Proof that I actually thought was really good, and it did not get a lot of play. And I think there was another movie with a similar name at the same time. And that got confused, but there was a cool story about math. Well, any math movie is probably worth seeing just because there's so few of them. It's like if you're in a town that only has one pizza restaurant, it's worth eating there, right? But yeah, I like that movie, and Beautiful Mind, which is not so much about, the math end of it, but it's still a part of it, and it's arguably a true story, is a good one. And there's been some others. There was a movie about Ramanujan that was okay. And somebody else mentioned Imitation Game, which is, more about Alan Turing as a person than the work itself. But yeah, we should make a list of good math movies sometime. All right, one more problem to talk about. This is something called the halting problem. This is another aspect of Turing machines, and this is, I believe, the reason why Alan Turing came up with the Turing machine model in the first place, was to study this question. Oh yeah, Good Will Hunting, definitely. Yeah, it's got one or two good scenes with chalkboards. So here's the question of the halting machine, the halting problem, right? So you write a C program for class, and it's supposed to, I don't know, see if a number's prime, or insert something into a tree, and inevitably one of two things happens. When you run your program, either eventually it exits or it goes into an infinite loop. Right? Sometimes you run it and it looks like it's broken, nothing's happening. It's because it's in an infinite loop. And maybe you did something like, while flag equals 1. And you did 1 equal sign instead of 2, so it's not checking to see if flag is 1. It's setting flag equal to 1, and this is a while 1 statement. Now it's going to run forever, right? So with a C program, sometimes they exit, sometimes they don't. And so a basic question is, if I hand you a C program and I tell you what I'm going to type in for inputs, can you tell me if that program is going to exit at some point? Or is it going to run forever in some kind of infinite loop? And for certain small programs, it's probably doable. If you understand C and the program's not very complex, you can look at it, if you see something like, while 1, do some stuff, and there's nothing that ever gets out of that loop, yeah, that definitely is going to run forever. And if you see a program that says, print something, set I equal to this, print something, and that's the whole program, you can look at that and say, yeah, that's going to exit. But in general, if someone just hands you an arbitrary C program, can you look at it and answer that question? That's what the halting question is. And it's originally asked on Turing machines. Given a Turing machine program and the contents of the tape initially, tell me if this machine will ever halt. Remember, if it goes to an undefined state, it halts. Otherwise, it just keeps, moving left and right and reading and writing and so on. So Turing's phrasing of this question was, given a Turing machine and the contents of the tape, can you tell if it's going to halt or not? Well, what do we mean by can you tell? What he meant was, can you write an algorithm to answer that question? Well, what is an algorithm? It's a collection of steps that you could describe as a Turing machine program. So this is about introspection. Can you make a Turing machine program that can look at another Turing machine program and tell you if it's going to halt or not? In a more modern version, could you write a C program that you give it the source code for another C program and it tells you whether that other program will halt or run forever? Okay, that's the halting problem. And it's a derivative of a problem that went back, to 1900, part of the set of Hilbert questions related to algorithms and computability. And so to study this question, there's this theoretical model of computation called the Turing machine. So you want to write a program, halts, that takes in a program and a set of input. And, at some point, you should either print out this will stop, or at some point, you should say this has an infinite loop. And this has not been solved. Nobody has come up with a program that you could give another program to and it can tell you definitively in a finite amount of time whether that other program will stop or not. And it has to give you the answer in a finite amount of time. Now, if it takes 1,000,000 years, that's still finite. But the requirement for this to be a solution to the halting problem is it's got to give you an answer in some finite amount of time. In other words, it can't run forever and not give you an answer. If that's the case, it's not a solution to the halting problem. And it turns out what Alan Turing was able to show was that you cannot solve the halting problem. You can prove that there's no way to do this. And this is back to another diagonalization argument like we used when we looked at cardinality of real numbers. And it's a very clever trick. And it's a trick that bothers me to some degree, to the point where I'm not sure I believe this argument. But here's the standard argument for why solution of the halting problem is impossible. So suppose that you have a solution to the halting problem. Here's my program. It's a function called halts. I will give it a set of C code, maybe, big long ASCII string, and a set of input, and it's going to eventually say, yeah, this program stops, or this program goes in an infinite loop forever. Okay, so here's the argument for why you can't do this. I could take this exact program and I can modify it. I can make a completely new program, and I'm going to call it bad program or something. And it's going to look just like my halting problem solver, except I'm going to do the following. Right after this print statement, I'm going to put a while loop that runs forever. And right after this print statement, I'm going to put an exit. And now I'm going to take this program and feed it to the thing that you say solves the halting problem. And I'm going to say, hey, tell me whether this program halts or not. Well, if this program runs on itself, it's going to eventually reach a conclusion. It's either going to say this program will stop or this program will run forever. But if this program would eventually get to the point where it says this program will stop, my bad program, after it says that, will go into an infinite loop. And your halting problem solver would have given me the wrong answer. It would have claimed that this program will stop when in fact it doesn't. It loops forever. And if your halting problem solver looked at this and decided it's going to go into an infinite loop, right, all the code is exactly the same except for these two statements and the name of the program. Your solver says, yep, this is going to go into an infinite loop, but in fact, when I run this program on itself, after that, it's going to exit. And again, your program would have given me the wrong answer. So this is a diagonalization argument. It's a case where we're sort of deliberately setting things up, we're stacking the deck, so that at the moment of resolution, we force something to go wrong. And this is the explanation you normally see in textbooks on discrete structures or conversations on the web about why the halting problem is not solvable. I don't like this argument. I have what I believe is a counterexample to this, which I've never gotten anybody in the mathematical community to look at seriously. But this is a sort of easier to get our brains around, I think, rendition of how you show that the halting problem can't be solved. The actual work for this is tied into like Gödel's completeness theorem and so on, and it's a fairly frightful endeavor to get into all of that, although it's on my life list. But the commonly accepted punchline is you cannot write a program which solves this halting problem, right? Which looks at another program and tells you whether or not it halts. And that's a believable result, right? Because if you had the ability to write a halting detector, think about what you could do, right? So your PA1, what did you do? You came up with a program to test Goldbach's conjecture, right? And it goes in a loop and it just keeps testing even numbers. So imagine that instead of just testing 500 numbers, you asked it to test numbers indefinitely. Just keep checking more and more numbers. But if it ever finds a number that can't be written as a sum of two primes, go ahead and do an exit. Well, now to answer Goldbach's conjecture, all we have to do is take your program and hand it to the halting analyzer and say, hey, will this program ever exit, or will it run forever? And if it says it's going to run forever, bingo, we just answered Goldbach's conjecture. Every even number can be written as a sum of two primes. And if instead it comes back and says, hey, this program's going to stop at some point, we've just said somewhere there's an even number that cannot be written as a sum of two primes. So certainly, if you could solve the halting problem, you would have an amazing tool that you could use to answer all kinds of interesting questions. So from that argument alone, it seems really implausible that such a program could exist. And there's these very complex mathematical proofs that basically say, yeah, that's the case. You cannot write something that solves the halting problem. But this leaves you with the question. This is a good ending point for the course at this stage. Is limits of computation. Are there programs that you cannot write on a computer? And apparently there are. There are real numbers you cannot print with a computer. How do we know that? Because the cardinality of the set of C programs is the same as the cardinality of the set of integers. Because any C program just looks like a giant integer if you just write out the bit values for all the characters. But the set of real numbers has a bigger cardinality. So there must be some real numbers that we cannot print with a C program. And that's potentially a little disturbing. So there's limits to what we can do with these Turing machines, right? Which is what all of our artificial computers are. There's definite bounds on their abilities. All right, so I'll leave you with that. I will post a topic of a summary topic list to think about, and we can talk about it on Friday in class. Cool. Have a good afternoon. I will see you next time.